Alrighty. So, we're going to continue in our unit of the applications of the integral. All right. So keep in mind our next assessment will be next week. All right. Next week. It will not. I'm thinking, and again, I'm a little fuzzy on the schedule, but like today we're going to be doing volumes of solids that have known cross sections, and we'll talk about what that means in just a second. Tomorrow we'll be doing like an AP kind of free response question day. If you notice at the end of your, not the end of your notes, but like after these notes, at the cross sections notes, there's like a bunch of free response questions, so we'll go through those tomorrow. And then Tuesday, some of you with me, some of you with Mr. Goff, will be doing arc length. And then I think that means Wednesday is going to be review for the test, and then Thursday will be the test. Something like that. Okay?
Or you can push your test.
So I think that's roughly what it's going to be. But the test is going to be next week on this unit. Okay? So make sure you've got that stuff down. All right? Today we're going to be continuing looking at how we can find the volumes of three-dimensional solids using calculus. All right? Up to this point, right? Up to this point, we have been starting with a curve, right? Like a function here, f of x, right? And we've taken the integral there, maybe from like a, or we, are looking at interested in a particular, finite region there from like a to b, all right? And so we know, for example, how to take the area of this region, right? And we know if we take that region with the area, and then we rotate it about the x-axis, or if we rotate it about the y-axis, okay, that kind of creates this three-dimensional solid, right? And that's what we've been doing so far. Today, what we're going to do is we're going to build a solid, treating this region as like the base of a solid, like something you would maybe like set down, okay? And then building this by using two-dimensional kind of like cross sections to build the solid up. So what do I mean by that? So let's just say, for example, that we were talking about, we wanted our cross sections to be triangles. So if I were to like slice this at any point, you would have a triangle. So what would that might look like? Well, you would have all of these like little triangles here kind of coming off the top of the shape, okay, like this. Okay, and if you can imagine, again, all these triangles, stacked together, obviously mine are spaced apart so you can see them, but all these triangles stacked together create this three-dimensional solid that's not quite like as symmetric as our rotations were and stuff like that, right? We don't really have a center per se. I guess we kind of have a center of the shape, but it's more just like this solid that's created. If you want like a better idea of like kind of what's happening here, because you don't like my drawing or whatever, and that's fine. If you just turn the page over, and I'll just give you a quick sneak peek at one of the problems we're going to be doing here. This is a solid with cross sections that are triangles again. So if you look here, right, here's a region in the coordinate plane, right? There's our x-axis, there's our y-axis. So we're two-dimensional right here. And what we would do then, again, we're going to use solids with cross sections that are triangles. Excuse me, the triangles are going to come up and out, okay? And then you can see it'll create this kind of shape right here, where our xy axis, there's our y-axis right there, there's our x-axis right there. And you can see these triangles that kind of build up, and there's that region, right? You can see the region right there. That region you see right there, that is this region right here. And so these triangles kind of build up, okay, and they get bigger. Why? Because the distance between these two lines gets wider, and so the triangles, as a result, get bigger, okay, because they're supposed to be equilateral triangles, okay? So it creates this solid. It's kind of hard to visualize. I'll show it to you better later on in class. All right, I have like an applet. I think it should work as long as the timing works out and stuff like that. As long as we have time, just kind of visualize it. All right, it's maybe kind of hard to see, not in motion or not like being built. Like when it's like there to there, it's kind of hard. But I do have like a little applet I can show you and stuff like that. Okay. So for now, the good news is, right, that the integrals here are actually super straightforward. It's for cross sections of area a of x, okay? So what we're going to do is stack up an infinite number of these like little cross sections to create these solids, all right? Taken perpendicular to the x-axis. So that's our clue that is with respect to x, okay? So if your cross sections are perpendicular to the x-axis, respect to x. if the cross sections are perpendicular to the y-axis, respect to y. Okay? So in terms of y, right? And you'll see here that all we're going to do is integrate from A to B the area, okay, of one of those cross sections. Okay? Now, we're going to be sticking to a few cross sections. So on the AP exam, cross sections will be squares, equilateral triangles, rectangles, semicircles, or a new function altogether. So sometimes they give you just a brand new function there, and so you don't have to worry about memorizing that formula kind of thing. Okay, but these are formulas to know. In other words, you must have these memorized. Okay? So some of these are pretty simple, pretty straightforward, right? The area of a square, for example, the area of a square is just side squared. Okay? The way these cross sections are created is that the distance from the curve to the axis there, that is the one full side length of our particular shape. So for a square, right, once you have one side of the square, you also have, well, all the sides of the square, and so you can easily find the area from just one single side. For an equilateral triangle, it's a little bit trickier, right? If we try and build an equilateral triangle, okay, if you have, a particular side, like that, all right, well, you've got the other sides here and here as well, but the problem is, to find the area of a triangle, it's 1/2 base, so we've got like a base here, but the height would be this altitude right here, whose length we don't automatically get. All right, but since this is an equilateral triangle, right, this altitude here cuts this equilateral triangle into two smaller triangles. And what kind of special right triangles do we create there? A 30, 60, 90 right triangle, right. And so if we say that this is x units long, then that means this right here will be x over 2. Okay. And then this is the side opposite the 60-degree angle, so that's going to be the √3 times x over 2. So the height will be √3x over 2. Okay, like that. Which means then the area of this triangle will be 1/2 times the base of x times the height of √3x over 2. And if you combine those, √3 times 1 is √3, 2 times 2 is 4, so there's the √3 over 4, and then x times x gives you x squared, so it's side squared, okay? Because again, x was the side, right? We used x for side length. So that's where that kind of comes from right there, okay? But again, that's a formula you'll need to have down if our cross-sections are equilateral triangles. Semicircle, all right, so we know the area formula for a semicircle. It's pi r squared is the circle, but then 1/2 of that, so 1/2 pi side over 2 squared, okay? And again, the reason why it's side over 2, okay, is because, again, if you're going from like A to B here, okay, if we're trying to find the area of a semicircle, okay, well, semicircles are going to kind of like build up like this off of our shape, okay? This distance right here is what measurement of the semicircle? It is a what of the semicircle? Diameter, right? And so this length, okay, this length that our function would be, its height off the x-axis there, that would be the diameter. So we have to take that side and divide it by 2. The function divided by 2, okay, that gives us the radius to then square it times pi, and then 1/2 of that because we only want a semicircle, so 1/2 of the circle. If you simplify all this, it ends up being pi over 8 times side squared, okay, which is maybe a better formula to memorize than all that jazz right there. Okay? And then finally, we can also talk about rectangles. Rectangles are side length times a height. And typically this height is some sort of given relationship. Okay? Because does the height of a rectangle depend on the side length, or like the base of a rectangle? Does the height of a rectangle depend on the base length? The answer is no, right? Okay, for a square, yes, the answer is true. I mean, the side and the base and the height are always the same, right? For an equilateral triangle, they will be related in this way. Right? For a semicircle, there's a relationship there. But for these area rectangle, the height can change, so we'll be given that relationship. Okay. There is a connection to the disk method. All right, there is a connection here to the disk method. So again, let me draw another picture here. So again, let's say we have our function here, f of x. And then I'm going to rotate this, right, about the x-axis. So this is kind of like going, back to stuff we did before. According to the disk method, if we rotate this about the x-axis, okay, the volume will be, well, pi times the integral from a to b of f of x squared dx. Okay, right. Bless you. Okay. By cross sections, all right. Well, remember, cross section, the generic formula for cross section is the integral from a to b of the area of one of our cross sections. With this solid, the way that it is, if we were to make a slice through this solid, what kind of cross section or what kind of shape would our cross section be? Not semicircles, full circles, right? If you were to cut through this shape, because we go completely around the x-axis, right, it would create a circle as our cross section. What's the area formula for a circle? Pi r squared, right? And so the volume will be the integral from a to b of pi times a radius squared, right? Of course, our function's radius is changing, our curve's, our solid's radius is changing there, and the radius is changing dependent on what? What determines the radius of this particular solid here? Well, what determines the distance from the center of our solid to its edge? Here's the center of our solid, right? And then there's the edge. What's that radius? It's f. Okay? It's f. It's f. All right? So this is the integral from, so we can, that pi, right, as a coefficient, we can bring that out front, and so it's pi times the integral from a to b of our function squared. And that is exactly what we've got right up here, right? It's the same thing. Okay? So solids with the cross sections of circles, okay? Or you can see how there's a relationship there, I guess I'll say, right? Disk method is like finding the volume of a solid with cross sections that are circles. Okay, in this particular sense. All right. Questions on anything so far? Yes, Gabe.
So that's the entire volume, right? For the one at A to B?
Yes.
Okay.
Okay, so for example, what's tricky here is that up in this case, okay, for this solid, for example, when I was using the semicircles, okay, the semicircles were limited from the x-axis up to the curve itself. And so they peaked like halfway between the curve each time. Here, for this situation, all right, our cross sections actually went kind of like, our curve is like kind of like between these two things almost. So it kind of like essentially like doubled, I guess, kind of thing what you were looking at. So it kind of switches the scenarios here a little bit, but that's the basic idea to connect the two. Okay. Other questions on anything? Okay. So again, this is a lot of like pre, kind of like, or I don't know, pre-write before we actually write, right, kind of thing. Okay, but let's actually get into an actual problem here and see how it plays out. All right. So, for example 10, we're going to find the volume of the solid whose base is the region bounded by the lines f of x equals 1 minus x over 2. So there's that right there, 1 over x minus 2. Sorry, 1 minus x over 2. 1 minus x over 2. Okay. And then And then the bottom curve is -1 plus x over 2. Okay, right there. And the line x equals 0, so the y-axis. So there's our region right there. Okay, so that's easy enough to identify. Okay, the cross sections are going to be perpendicular to the x-axis, and they are equilateral triangles. All right, so since we are perpendicular to the x-axis, that means we're going to be integrating with respect to what? Okay. Very good. And so then let's take our side here. And so the side of our triangles here, you can see again, there's our base right there. This is our base of our shape, okay? We're looking kind of like top down on top of our shape, and the triangles are going to come up, down, like that, up, and down, and build this solid, okay? And now we kind of have this like skewed look at it right there. All right, that's what the solid would look like, okay? So the side of one of these triangles is determined by what? It's the distance between what? The side of one of our triangles. So like you can see, here's like a little representative triangle right here. It's kind of hard to see with there. Okay. The side length of one of our triangles is determined by what distance? Oh dear, I've lost them. Okay, so let's go take a step back here then. All right, let's take a look at the volume formula here. Right, going back to what we know, the volume formula, okay, for our solid with known cross sections is the integral from a to b of a of x dx. All right, because we're with respect to x here. Let me maybe ask an easier question. All right, what are our limits of integration going to be here? From what to what? 0 to 2. Okay. Very good. Okay. What's our area formula? Since it's equilateral triangles, it's going to be side squared times root 3 over 4, right? So side squared times the square root of 3 over 4 dx. Okay. Again, if you look here, you've got one of these triangles kind of shown in here. Okay? And this triangle, right, is between what two curves? F of x and g of x. Exactly right. And so the side length will be determined by f minus g, this distance here. F take away g. So f minus g, which is equal to 1 minus x over 2 minus -1 plus x over 2. Okay. And of course, we can combine these together, so we might as well do that to make life easier for ourselves. Instead of subtracting this, we'll make it add the opposites. 1 plus 1 gives us 2. Negative x over 2 plus a negative x over 2 is negative 2x over 2, which is really just, well, minus x, so 2 minus x. Okay. So the distance between these two curves is the length 2 minus x. That means the sides of our equilateral triangles will have always the length 2 minus x there. And so for our integral, we'll do the integral from 0 to 2, 2 minus x squared. Okay, actually I should pull the root 3 over 4 out front here. Okay, squeeze that in front there. All right, I'll just rewrite the whole thing. Okay. I decided to rewrite it there. All right, and yes, we're going to actually integrate this. Okay. I see two options at least for integrating this thing. Option 1, what could we do? Calculator. Without a calculator, I see 2 options. So 3 options, I guess. Without a calculator, what could we do? Do it. All right. So yeah, we could do 2 minus x, just square it out, right? Okay, and that's what I think I'm going to do here. Alternatively, you could use a u substitution if you wanted to, let u equal 2 minus x, and go from there. I think I'm just going to do a, just like straight up kind of multiply it out. So I'm going to kind of go down here now and say root 3 over 4 integral from 0 to 2. Okay, if we square 2 minus x, remember it's 2 minus x times 2 minus x, right? Yeah, bless you. Okay, just like FOIL that out. Okay, do not give me 4 minus x squared there, please. Do not give me 4 minus x squared. All right, so it's 4 minus 4x plus x squared dx. Which is equal to root 3 over 4, and then let's see, it's going to be what, 4x minus 2x squared plus 1/3 x cubed, evaluate from 0 to 2. Okay. Our lower limit is 0, and so our lower limit, will we have a lower limit? If I plug 0 in here, here, and here, that's all going to be 0. Then times root 3 over 4 is still 0. So the lower limit is gone. We don't have to worry about that. We can just plug in the 2. So we root 3 over 4 times, let's see, 8 minus 2 squared is 4 minus 2, times 2 is 8, so minus an 8, and then plus 1/3. Actually, 2 cubed is 8, so we'll say 8/3. Okay, so it's going to be, that's going to cancel the 8 minus 8. 8/3 times root 3 over 4. That'll give us 8 root 3 over 12, which simplifies to divide by 4, so 2 root 3 over 3. Good times. All right. Let's try another one. That was fun. Okay. Questions on that one, I guess. Let me stop before I go on anymore. Yes, Simeon.
Why wouldn't you just use the normal volume formula like the disk method?
Because what kind of shape would the disk method create? That would involve a rotation, right, about the x-axis. Would that create a solid that looks like this? No. It would not. So it's a different solid altogether that we are creating here. Okay. The solids cross sections for this shape are triangles, equilateral triangles. For a rotation using disk or washer method, we're going to end up with, well, disks for our cross-section, circles, or we're going to end up with washers, donuts, I guess, or whatever you want to say there, okay? So for this one, though, we want the triangles. Other questions? All right, so let me see this again. All right, let's try another one here. Oh, question, sorry, Long.
Why would you do f minus g side but not like g minus f?
Why not g minus f? Because g minus f, well, I mean, I guess in this situation, it would be the same thing, right? Because we're going to end up squaring it. So in this case, it doesn't really matter, I would say. Yeah. But, and I guess it wouldn't really matter for squares either, because you're going to end up squaring it, and it wouldn't really matter for semicircles. But it would matter for rectangles, though, because rectangles you don't, well, you could maybe get away with it with rectangles potentially, but yeah. Why do we do f minus g in this case? Top curve minus bottom curve to get that distance. You want it to be a positive distance. If you do g minus f, you're going to get a negative distance, which is still okay because you're going to end up getting, you're going to square it anyway. But so you could get away with g minus f there. Okay. Yeah. Okay. All right. So anywho, let's take a look at another one here. Find the volume of a solid whose base is the circle x squared plus y squared equals 9, and where cross sections area are all squares whose sides, semicircles whose diameters, and rectangles whose height is always 3 times the side length, and whose sides lie perpendicular to the y-axis on the base of the circle. So essentially what this is trying to say here is, there's our region, okay, and then find its volume when you have squares for the cross-sections, semicircles for cross-sections, and then rectangles, whose heights are always 3 times the side length for the cross-sections. All right, so let's sketch what this looks like. This is a circle centered at the origin with radius. Very good, yes, 3, okay. just got done talking about this stuff in my geometry class, actually. Geometry class. Okay, so there's our circle. Since our since our cross sections are going to be perpendicular to the y-axis, that means we get to do this with respect to
Why?
y.
Why? Why?
All right. So our curve is x squared plus y squared equals 9. So if we want to get that in terms of y, that means we're trying to solve for what variable? X. So x squared equals 9 minus y squared, and so x equals plus or minus the square root of 9 minus y squared. Is that plus or minus necessary in this problem? Are we concerned about both positive x and negative x values for this region? Yeah, we got to encompass the full circle here, so we need to have both positive and negative, okay? The positive root 9 minus y squared, that's this part of the circle. Okay, that's the positive root 9 minus y squared. And then the negative root 9 minus y squared is this part of the circle. Okay, that's this part of the circle. That's half. All right, and again, using our imaginations, all right, we're going to kind of picture squares, all right? So the squares, the side length of the square will be determined by the distance between these two curves, all right? Or I guess I should really talk about it this way, because we're going with respect to y, so the cross sections have to be perpendicular to the y-axis, right? Perpendicular to the y-axis, so this way, okay? So our square, if it has a side length of this, that means its height will come off the circle that same amount, right? Same thing here. Okay, so this distance right here will be the side length of the square. It will come up like that, and then we're going to just do you would do like, you know, an infinite number of those squares there. You're going to have like a teeny tiny square down here at the bottom, right? And teeny tiny until you get down to the very end there. Okay. So it creates this solid. And again, I'll be able to show you a picture of the solid later, not right now, just because it's hard to switch between the two things, and I don't want to mess up the video, especially because Mr. Goff's counting on this video to work today because he's got his 4th block calculus students that won't have him there. So, hello, 4th block calculus students. All right, so anyway, let's go to letter A here. All right, what's that?
Is this just a cylinder?
So it's not quite a cylinder, no. The semicircle one would be, well, again, I say not quite. And again, I'll show it to you. You'll see it's not quite a cylinder. So, anywho, let's take a look here. So again, volume equals the integral from C to D of area of y respect to y. And again, for letter A here, we're doing squares. Okay, what is the area formula for a square? Side squared dy. Okay, so the length of our side here, our side's going to go from this curve to this curve, right? Okay, so from there to there. Okay, so we'll do right curve, root 9 minus y squared, minus left curve, negative root 9 minus y squared. Which is this 2, right? Plus positive, so it's going to be 2 root 9 minus y squared. Alrighty. And so we just plug our side in here to the formula. The integral, we're going to integrate from what to what? What are our limits of integration going to be here? Negative 3 to 3. Yeah, negative 3 to 3, because we're going from left, or not left, right, we're going from bottom to top here. We're going to integrate from negative 3 up to positive 3 there. And then our side, we already said was 2 square root of 9 minus y squared. Excuse me, squared.
Bless you.
Bless you. Okay. And you can simplify this if you want to, right? Integral from negative 3 to 3 of 4 times the quantity 9 minus y squared dy. You can pull that 4 out, and I'm not going to integrate this one. All right, we'll just let it for there. Okay. I think you can go from there, right? Iffy. All right. Well, if you want me, I'll go over it with you later. Oh, you're good? Okay. Next, letter B, we want to do semicircles. Okay. All right, in this case, the semicircles, the diameters of the semicircles are this. So again, you can imagine kind of like, semicircles kind of arcing up in here. Can anyone kind of picture what shape that will be? A hemisphere, yes, half of a sphere, Okay, well, this kind of is the shape. So I mean, you could ostensibly, right, use the formula, I think, for half of a sphere, and that would be, okay to do too. But let's set this up using calculus. Let's make it more complicated than it needs to be. All right, semicircle formula: pi over 8 side squared. So I'm going to pull that pi over 8 out front because it's a coefficient. And again, we're going to integrate from -3 to 3. And it's going to be side squared. So what's our side? Well, it's again that 2 square root of 9 minus y squared dy. So the only thing that's changing here, because our region is staying the same, right? And the all of our cross sections are staying, perpendicular to the y-axis. The only thing that's changing is the kind of cross section that we're using. And so what changes as a result of that? The area formula for those particular cross sections. For the square, it's side squared. For the semicircle, it's pi over 8 side squared. Okay? For letter C, rectangles. Okay, remember that for the rectangles, it's side times the height. Okay, again, respect to y here. Well, we already know the side length of our rectangle, what it's going to be, right? We determined those already. So it's going to be, again, the integral from -3 to 3 times the side length of 2 root 9 minus y squared. But then the height, what are we told is true about the height of these rectangles? 3 times the side length. What's the side length? 2 root 9 minus y squared. What's 3 times 2 root 9 minus y squared? 6, or 3 times 2, right? You just make it 6, okay, root 9 minus y squared. Okay, that's, 3 times 2. dy. And so at this point, right, again, I'm not going to do the entire integral here, but I'll kind of help us out. Right, this is all one big product, so the 6 and the 2 can multiply together. You can pull that 12 out front. Root 9 minus y squared times root 9 minus y squared is just going to be 9 minus y squared dy. And then again, you can go from there. That's the idea. Okay? So, yes, Gabe?
So you're basically using that circle to create a bunch of different types of solids?
Yes, several different types of solid depending on the cross section, right? Depending on the kind of cross section there. And unfortunately, like those solids that we're creating there, they don't really have any like easy examples that we would see, like I say, in everyday life. Like they're kind of like funky looking a little bit, and that's why it's maybe even harder for us to visualize because we don't have any sort of like, paradigm for it, kind of thing. So yeah.
Can you explain how to get the height?
The height, like you mean like oh right here?
Like the 6 root 9.
Okay, like this part. Gotcha. So the height, okay, whereas in these other ones, right, the only and the other cross sections, right, we had like kind of like one variable, we'll say, right, Chase? For example, in the squares, it's just side squared. We know what the side is, it's that. So it's just going to be this thing squared, right? Semicircles, it's pi over 8 times side squared because a semicircle you can rewrite in terms of a single variable. But for a rectangle, the rectangle's side does not always depend on its height, right? Whereas a square, the side of a square is always the height of the square too, right? So that's why it's just side squared. But for a rectangle, side and height are independent of one another. And so most of the time you'll be given some sort of relationship for the height, and it relates back to the side in this case. So in fact, if you just read it here, rectangles whose height is always 3 times the side. So it's side times height, side times 3 times another side. So it's just going to be 6 root 9 minus y squared. That's all. Okay. All right, we're going to turn the page here, do one more example together. All right, and that will be this example 12 here. That is a non-calculator question, and we can barely read. All right, but it's there.
Find the area of all, we can do that.
All right, right.
We can do this. We can
Yes.
do this.
So I will. Let's see here. Let's just jump to letter B, and then I'll have you guys try A and C there on your own, and we'll go over that kind of thing. Okay. My goodness. All right, so I believe these two curves here are supposed to be y equals the square root of x. Yes, and y equals x over 2. 1/2 x, that looks like what it's supposed to be. Okay. So find the area of R, not going to worry about that for right now. But let's do letter B here together because that is another solid with known cross sections. Okay. So the region R is the base of a solid. For the solid, the cross sections perpendicular to the x-axis. So perpendicular to x-axis means we're doing it with respect to what? Respect to x. Are squares. Okay, they were very kind to us here. All right. So let's, again, I'm going to skip letter A for now. We'll just jump down to letter B. So volume for solids and known cross sections, integral from A to B of the area. Okay. And then again, we're doing squares here. Okay. The area of our cross section with respect to x. Okay. So our cross sections are going to be perpendicular to the x-axis. Right? So we're going to be going, our cross sections are going to go between here. Okay, and again, I space these out, but you imagine, right, there's going to be squares like at every instant here, and they're just going to pop up. Okay, like up, over, down, up, over, down, up, over, down kind of thing. So what is determining the distance, the length of our side here? It's the distance between what? The two curves here, the two curves, right? Okay, so this side length here is determined by the two curves. Okay, and so our side here is going to be equal to, and in fact, maybe I'll put it down here. The side length is going to be equal what curve minus what curve? Root x minus the x over 2, yeah. Okay, and so, again, for this case, since we're using squares, it's going to be the integral from A to B of side squared, which in this case, okay, the integral from, what are our limits of integration going to be? From what to what? 0 to 4. And again, the side is going to be root x minus x over 2, quantity squared. Okay, and so there's our setup. All right. So to multiply this out, well, sorry, we need to multiply this out first, right, before we can take the integral, right? This is not in a format that we can take the integral, and I don't think a u substitution here would not really be helpful. So we'll really need to use, we'll want to square this out, okay? So let's go ahead and do that. So integral from 0 to 4, and let's see. So if we FOIL this out, again, it's root x minus x over 2 times root x minus x over 2. Okay, so we're going to get just x, right? When we do the first, there you go. So x, and then it's going to be minus, now root x times x is going to give us x to the 3/2 over 2, but they're going to have another minus x to the 3/2 over 2, so it's going to be just minus x to the 3/2. Okay, again, this one and this one together will give us just a single x to the 3/2. And then x over 2, minus x over 2 times minus x over 2 will be plus 1/4 x squared. Okay, so there it is all multiplied out. All right, and of course it asks us to actually integrate this and stuff, so I'll go ahead and do that here. So you get 1/2 x squared minus 2/5 x to the 5/2 plus 1/12 x cubed, evaluate from 0 to 4. Okay. Our lower limit of integration, thank God, is 0. So that means I'm going to plug 0 in for all of these. That's going to be 0, right? And so I just got to worry about plugging the 4 in. Actually, let me just go ahead and do this. So, well, you know what? Okay, and again, we can, 4 to the 5 halves. I don't know why I put a 2 in there. Okay, and so again, you can leave it like that, right? Because this is non-calculator, it's free response question, so you can stop right there. But let's see here, 16, 8. So 4 to the 5 halves. Well, the half part means we're going to do what? Square root. So it's really just a 2. And then 2 to the 5th. 4, 8, 16, 32. All right, and then 32 times 2/5, though, so it'll be minus 64 fifths. And then 4 cubed, 16, so 64 over 12. Okay, and then I don't feel like simplifying the fractions anymore, but there you go. Okay, enough, right? Okay. And you guys can get common denominators and stuff like that from there. All right. So why don't you guys go ahead, try A and C. Go ahead, take, like 2 seconds there. At least set them up. All right, at least set them up. But I would say also, take the actual integrals in this case just to make sure we're able to do it all. Okay, so A and C, except for letter C, of course, says write but do not evaluate. So really just A that you're supposed to figure out, and then C, set up but do not evaluate there. So go ahead and give those a try. Okay. So, should have gotten something like this. Don't forget the pi in front for letter C, right? And then 4/3 for letter A. We use the pi. All right. Questions on any of that? Lander, yeah?
Should we do 32 over 6? 32 over 3?
32 over 3? And let me see.
Oh, no, never
You
mind.
good? Okay. Because I took the square. Yeah. Okay. Well.
So you're doing
Yep. Okay. All right. So let me take some time here and kind of show you guys. Sorry, video folks, you guys aren't going to be able to see this part.